Next, for example 6, we're going to solve a trigonometric equation with a calculator. So we're going to use a calculator to solve tan of theta equals -2, and our theta has to be on this interval. And we want to make sure our calculator is set to radians. So if I have tan of theta equals -2, I'm going to take tan inverse of both sides, or arctangent. I probably should say arctangent. Arctangent of both sides, so I get theta equals arctangent of -2. And when I plug that into my calculator, I get theta is -1.11 radians. Well, here's the problem. This isn't between 0 and 2 pi. So if I add, I'm somewhere down here, right? I have like negative radians. So if I add pi radians, because tangent has a period of pi, I will find something else with the correct value because we're negative. That means we've gone downwards. So if I have -1.11 and I add pi to that, that's going to give me about 2.03 radians. And if I see that I have 2.03 radians, we'll just say that's over here, right? We'll say it's over here. Might not be. No, it's definitely not because it has to be in quadrant 1 or quadrant 3 to be. Nope, it has to be in quadrant 2 or we're in quadrant 2 or quadrant 4 because tangent is negative. Sorry for that confusion. Tangent is negative, which means x and y have to have opposite signs. So we're in quadrant 2 or quadrant 4. So over here, maybe that's where our first theta is, but that means I also have another one if I repeat another pi. So if I take -1.11 plus 2 pi, that's going to give me about 5.17 radians. So I have two possible values from 0 to 2 pi radians. For example 7, we're going to solve a trigonometric equation in quadratic form. And we're going to do that by factoring, right? If I had 4x squared minus 1 equals 0, you'd be like, oh yeah, this is a difference of two squares. So I'd have 2x plus 1 times 2x minus 1 equals 0, and then I could solve for x. We're going to do the same thing, except now, instead of x, we have sine. So this is going to factor to 2 sine of theta minus 1 times 2 sine of theta plus 1 equals 0. So we set both of these equal to 0 using the zero factor property. I get that sine of theta equals a positive 1/2, or sine of theta equals a negative 1/2. And sine is defined, we want the answers between 0 and 2 pi. So I look at my unit circle and I say, okay, where's sine of theta? So the y value 1/2. Well, it's positive 1/2 at pi over 6, and it's positive 1/2 at 5 pi over 6. Then I go to where is sine of theta negative 1/2? Well, that's going to be at 4 pi. Sorry, that's going to be at 7 pi over 6, or, staring at my unit circle, 11 pi over 6. So our solution set is theta equals pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Let's practice factoring trigonometric equations in quadratic form again. So I'm going to solve this equation. 3 cosine squared theta equals sine of theta squared. So I have 3 cosine squared theta equals sine of theta squared. Well, sine of squared theta plus cosine squared theta equals 1. So if I get sine of theta by itself, I have 1 sine of squared of theta equals 1 minus cosine squared theta. This is one of our Pythagorean identities. So I'm going to substitute, instead of sine squared, I'm going to take 1 minus cosine squared theta. If I add cosine squared to both sides, I get 4 cosine squared theta equals 1. So 4 cosine squared theta minus 1 equals 0, and then I can factor. I now set each of those factors equal to 0. So I have cosine of theta is a negative 1/2, and cosine of theta is a positive 1/2. So first I'm going to go to my unit circle and say, okay, where's my x value? Because that's what cosine is, a negative 1/2. Well, that's going to be at 2 pi over 3 and 4 pi over 3. And then I look at where my cosine is a positive 1/2. That's at pi over 3 and at 5 pi over 3. So my solution set is 4 possible thetas, which is 2 pi over 3, 4 pi over 3. Maybe I should have written this in order first. So pi over 3 first, and then 5 pi over 3. So it's repeating every pi over 3. Not every pi over